Oh, hey. Right now, we're looking at a wire. Because magnets. So, inside it are a bunch of positive and negative charges. The negative charges are electrons, and the positive charges come from protons in the wire. They're all packed in there with the same density, though, so the wire doesn't have any charge on the hull. It's neutral. Also, the positive charges are stuck. They can't move around. But the electrons can. If you put in some voltage, the electrons will flow across the wire. And the wire stays neutral. That's an electric current. So, let's make another electron appear, because we can, I guess. Ta-da! Nothing happens, because our wire is still neutral. Even if you wave it around a lot, nothing. Let's try turning the current on. Still nothing, until we move the electron. Suddenly, there's a magnetic force that's pushing and pulling on the electron, depending on its motion. But why? Let's take a look at the wire in space-time. Actually, let's just look at space-time real quick first. Here are an electron and proton at rest. Don't wake them up. And here's what they might look like in space-time. Two parallel lines. At every point along the proton, you can see it's the same distance across from the electron in space. So, it's not moving. Oh, and same goes for the electron. Now here's the two of them just moving at constant velocity. And again, this is what that might look like in space-time. At each point in time for the proton, it gets closer to the electron until it crosses it and keeps going. Same thing goes for the electron, and you can kind of see how this gives us the motion. Now it's time to take a look at what our wire could look like. That's it, the black rectangle. It's drawn with time going up and down from the wire's point of view, and space going across it, so that's the length of the wire in space. Now let's draw in the charges. So we got some protons, all at rest, and all with the same point of view as the wire. And then the electrons, with their moving frame of reference. Now here's something. If we just look at one moment in time for the wire, and glide that in the time direction, we get our current. Electrons move to the left. Also, they stay the same distance apart, so the wire is still neutral. This animation is supposed to show the equal spacing, or something. So that's all good. But the reason we did all this was because we wanted to know why a current had an effect on a moving electron. So let's add that moving electron to our picture, at least. There. It's moving along with the other electrons to make things easy. So, how do we see from its point of view? Like that. It's just like our two moving particles. We can look at either one as at rest if we want to. So, do you see anything different about the wire now? It's not neutral anymore. The charge density's changed up. Like right here. The two charges in the middle are lined up, but the other protons are clearly stretched out. Or maybe the electrons are squished. And it's the same here again. Stretched out protons. But space-time is weirder than that. When the protons should be stretched out, like they are here, then they actually end up being squished when you see them. There's always this weird reverse effect when we draw these pictures. And it happens that a way to account for it is to make the unit of time an imaginary number. Didn't want to put math into this at first, so I'll just make this quick. We'll draw an orange arrow between a pair of protons as we see them now, and another for how we saw them before. They make a triangle. So then we can say this. The new distance squared equals the old distance squared plus that white line squared. Thanks, Pythagoras. Alright, but what is that white line? If you kinda look at it, it's the length of time on the proton. So if we add in that imaginary I, then the term from the white line goes negative. And you can already see, now the new distance is shorter than the old distance, because the t is taking something off the old distance. Making time imaginary always seems to have this kind of reverse effect, at least when we draw the pictures this way, but it gets the right answer. And that's all the math. The final idea is the new distance is shorter, even though it was bigger in our picture before. So that makes the positive charge squished in our frame of reference. You could say they're denser. Even with the electrons, the wire has more positive charge per length. So the wire's definitely positive now, and it'll pull on any electrons with reference frames like ours. Like that one. Maybe that one? Wah. So this might be why a rock with a bunch of moving electrons in it, like a magnet, can push and pull on another clump of spinning electrons, like another magnet. Then,